Hi, Honors Algebra 2 students. We're in Chapter 5, Day 10 Notes, and we're going to focus on models of quadratic functions. So let's read our model problem first, and then we'll dive in and get started on the details. Phoebe Small is out Sunday driving in her spaceship. As she approaches Mars, she changes her mind, decides that she does not wish to visit that planet, and fires her retro rocket. The spaceship slows down, and if all goes well, stops for an instant and then starts pulling away. While the rocket motor is firing, Phoebe's distance d from the surface of Mars depends by a quadratic function on the number of minutes t since she started firing the rocket. All right, part A. Phoebe finds that at times t equals 1, 2, and 3 minutes, her distances are d equals 425, 356, and 293 kilometers respectively. Find the particular equation expressing d in terms of t. Okay, so you may recall with our other model problems that even when we're asked to find the particular equation expressing d in terms of t like we are here, there's a lot of other work that we require you to show us first. So the first thing you need to do is define your variables. In other words, the process we're going to go through is very similar that we did for linear model problems. So in defining our variables, they were really nice to us. They basically gave them to us in the paragraph, the initial paragraph. So t is the number of minutes since firing the rocket, and d is the distance from the surface of Mars in kilometers. So take the variables that were given and make them very, very, very specific. So don't just say that t is time or the number of minutes. It's the number of minutes since something happened. And in this particular case, it's since firing the rocket. And the same thing with the distance. It's not just distance, but it's distance from something, from the surface of Mars, and specifically it's measured in kilometers, which we're given to right here. So be very specific with your variable definition, and that, first of all, we require it, but secondly, it will help you later on in the problem. All right, the next thing we require in the process is for you to write your ordered pairs. So as it says here, your distance depends on the time. So time is your independent variable and distance is your dependent variable. And so when we take the information that we're given about the various times and minutes and we put them together, we've got the three ordered pairs that we have listed here. So 1, 425, 2, 356, 3, 293. All right, and then the next thing we need to do is write our particular equation and show all the work that we need to in order to support that. So in the prior lesson, you learned how to take three ordered pairs that were on a quadratic function and use them then via a system of equations to come up with that quadratic function. So we're going to do the same thing here. So what I would ask you to do, I know I have all this written out, but what I would ask you to do is now pause the video, take these three ordered pairs and what you learned in the prior lesson and see if you can come up with the quadratic function, and then check your answer in just a moment. All right, let's talk through the work for coming up with the quadratic function and see how you did. So I took a general quadratic function and I rewrote it in terms of t and d. So in other words, t is where, maybe we are used to putting our x variable, and d is where we're used to perhaps putting our y variable. So just very, very generically, and you don't have to write this part down right here, but I usually do for my students. So we're working towards at squared plus b times t plus c is equal to d. So if we take the ordered pair 1, 425, and we plug a 1 in for every occurrence of t, in other words, that's my quote-unquote x variable, and I plug in a 425 for my d variable, or if you're used to thinking about it in terms of y, I would come up with a plus b plus c is equal to 425. All right, if I take 2, 356, I plug in a 2 for t in every occurrence of t in that equation, and I plug in a 356 for d, I get 4a plus 2b plus c is equal to 356. And then if I do the same thing for the final ordered pair, plug a 3 in for every occurrence of t, plug a 293 in for d, I get 9a plus 3b plus c equals 293. All right, so now I have my system of equations. Notice it's 3 equations, 3 variables. So no, you do not have to manually solve that system of equations for A, B, and C. You can set it up via a matrix, and you can solve it with one of our matrix methods that we learned. So you can either use inverse matrices and use your calculator, or you can set it up and use our REF on your calculator. I typically use our REF, but that's just my personal preference. So if I use our REF, I'm going to set up my coefficients and my constants in one matrix. So I've got, 1A plus 1B plus 1C is equal to 425. 4A plus 2B plus 1C is equal to 356. 9A plus 3B plus 1C equals 293. So notice I show my matrix that I'm going to enter on my calculator. I do RREF on that matrix. And then this is the matrix that results from it once I plug that into my calculator. So if I interpret this, this is saying that 1A is equal to 3, 1B is equal to negative 78, 1C is equal to 500. And so if I go back to my quadratic function and I plug all of that in, I plug in a 3 for A and a negative 78 for B and a 500 for C, then I get that my distance equation is equal to 3t squared minus 78t plus 500. All right, now I wrote all of this out ahead of time because it follows the approach that we learned in the prior lesson. So hopefully if you needed to, you pause the video to work things out and follow along and check your answers. And again, if you need to pause the video to get everything down before you proceed with the other parts, that's fine. But this is basically what was covered in the prior lesson. And as far as what you need to show, just to reiterate or reinforce the steps that you would need to show when we approach model problems, the first thing you're going to need to do is you're going to need to write down your variable definition. Then you're going to need to write down your ordered pairs. And then you're going to need to come up with your, in this case, quadratic equation down here. But in doing that, you need to show whatever work is necessary. So for linear model problems, it was calculating the slope and then writing the equation. For quadratic model problems, it's going to be to take your 3 ordered pairs, write your system of equations, then use a matrix method to solve that system of equations, since we certainly don't require you to do it manually. So show whatever work is associated with that. So in this particular case, it would be showing the matrix that results from the system of equations, showing doing RREF on it, showing the resulting matrix from your calculator, and then interpreting that answer and putting it into your final quadratic function. All right, in part B, it says find the d-intercept and tell what this number represents in the real world. So all I did here is just recopy our quadratic function that we came up with in part A. And then if we think about it, and I wrote this very, very generically, our distance is going to depend upon the time. So in other words, the distance that Phoebe is from the surface of Mars is going to depend upon the time that has passed since she fired the rocket. And so if you need to do a quick visual for this to determine, which intercept you're really figuring out, if it's the d-intercept in this case, it's going to be, here on your y-axis, so to speak, so you're finding the y-intercept. So I would ask you to pause the video, find the d-intercept in this case, think about what it represents in the real world, and then restart the video so you can check your answer. And I'm going to be following this approach for quite a bit of this particular example because you know how to do all the parts and pieces, so to speak, of this particular model problem. It's just a matter of guiding you through the process. And so on most of these parts, I'm going to do a little introduction. I'm going to ask you to pause the video and then restart it and check your answers. All right, so let's see how you did. If we are finding a y-intercept, or a d-intercept in this case, that's going to be 0 comma something. So if we plug a 0 in for t, we're going to get 500. So our ordered pair answer for the d-intercept is going to be 0 comma 500. Now when we tell what it represents in the real world, if we go back to our variable definition where hopefully we were very, very, very specific, it's a matter of plugging in these values and then using your units of measure and doing an interpretation from there. So again, the more specific you are with your variable definition, the easier it will be to interpret the d-intercept in this case. So what it means is that Phoebe is 500 kilometers from the surface of Mars when, t is equal to 0, which means when she fires her rocket. In part C, according to the equation, where will Phoebe be when t equals 15, when t equals 16? Does this tell you she's pulling away from Mars when t equals 16 or still approaching? And I just recopied the original quadratic function again so we have it in front of us. Now what I would do is once again ask you to pause the video and find out the answers to the questions that are being asked and then check to see how you did and restart the video at that point in time. All right, let's see how you did. So again, this is our general quadratic function from part A. So when t equals 15, if we plug that in for every occurrence of t into our equation, and you can use your calculator, you're going to get that when t is equal to 15, the distance is 5 kilometers. Again, you do need to show what you're doing to get that answer, but once you show plugging in t equaling 15, you can plug it straight into your calculator and get 5 kilometers. And then when t is equal to 16, we do something comparable, and then we get that the distance is equal to 20 kilometers. All right, so to answer the question, does this tell you she's pulling away from Mars when t equals 16 or still approaching? This tells us that Phoebe is pulling away from Mars when t equals 16 minutes because her distance from the surface of Mars at that time is greater. It's 20 kilometers. Notice it's 20 kilometers. So her distance from the surface of Mars is greater than it was when t equals 15 minutes, which at t equals 15 minutes, it was 5 kilometers. So again, the more specific you are with your variable definition above, the easier it is to interpret your answer in part C. And make sure you put your units of measure on here for your distances, and then be as specific as you can in your explanations to answer that final question. Part D, does your model tell you that Phoebe crashed into the surface of Mars, just touches the surface, or pulls away before reaching the surface? Explain. So let's talk about how we could figure that out. So as we looked at before, if we have Phoebe's distance from the surface of Mars on our dependent axis and the time since she fired her rocket on the independent axis, and we know it's a quadratic function, if you think about it, she started up here. Our d-intercept we found was 500 kilometers from the surface of Mars. If she's traveling in her rocket towards the surface of Mars, we could figure out, does she come down here and then before she reaches the surface, turn around and go back, so her distance is increasing. Again, her distance from the surface of Mars is increasing. Or does she come down here and touch the surface of Mars, which would mean her distance from the surface of Mars is 0, and then her distance starts increasing because she's getting farther away from it. She turns around and goes back. Or does she come down here and crash into the surface of Mars, unfortunately, so to speak. So if we find the vertex, because that would be the point at which she, quote unquote, turns around, so to speak, and goes back, and we figure out, the 3 scenarios it could be. If we figure out that vertex, that will help us then interpret what happened in this scenario. So I would ask you to pause the video. You know how to find the vertex of a quadratic function. So I would ask you to pause the video, find the vertex, interpret what it means, and then restart the video and see how you did. All right, so let's see how you did. I have the quadratic function written down up here again just for our reference. And if we find the coordinates of the vertex, again, I use t and d over here instead of x and y because that's what we're using in our variables within our quadratic function. So t is equal to the opposite of b all over 2 times a, so we get that t is equal to 13. To figure out the distance associated with that, I'm going to plug a 13 in for every occurrence of d, and I can plug that into my calculator and get that d is equal to -7. Again, you just need to show your algebraic work for that, but you can use your calculator to do literally the calculations. So the vertex is 13 comma -7. Now let's interpret that and see what that means. So this is saying that at 13 minutes after Phoebe fired her rocket, her distance from the surface of Mars is -7 kilometers. So if we interpret that, what that means is that Phoebe crashed into the surface of Mars because 13 minutes after firing her rocket, she is 7 kilometers into or beyond, however you want to think about it, the surface of Mars. So, if she had turned around before she reached Mars, she would have a positive distance right there. If she had just touched the surface of Mars, she would have had a distance of 0 right there. But since it's negative, that means she crashed into the surface of Mars. All right, now as a side note, as I tell my students every year, I know we may be concerned about Phoebe since she crashed into the surface of Mars, but I will tell you that Phoebe makes a reappearance throughout this course, so be looking for her. You will find that she makes a reappearance, so you'll just have to be waiting on that to happen. Part E, draw a graph of this function based on your answers to the above questions. In what domain do you think this quadratic function will give reasonable values of d? Modify your graph by using a dotted line for those parts of the graph that are out of this domain. So once again, what I would ask you to do is I would ask you to pause the video, write down ordered pairs that you're going to graph, figure out your labeling of your axes and your scaling of your axes and plot that quadratic function, and think about what it's asking you about the domain. What would be reasonable within this context that we've been given for what the domain would be, and figure out what that would be. Once you've gone through all of that and done your graphing, again, while you're doing that, I would ask you to pause the video. Once you've done that, then restart the video and see how you did. All right, so I had the video paused for quite a while I wrote out the answer to part E. So hopefully you did as well. Hopefully you did this on your own. So what I have my students do when we graph these model functions, I have them make a list of all the ordered pairs that we could possibly graph. So here's what I mean by that. We've got 3 ordered pairs from the original scenario that was given to us. In one of the parts of the problem, we found the y-intercept, so I've got that listed. And then in one of the problems, or parts of the problem, we found when t was equal to 15 and 16, what the distances were from the surface of Mars. And then in the part above, we actually found out the vertex. All right, so now you may ask, well, what is all of this over here? Well, we need to find the x-intercept. And often on these model problems that we do, we're going to have to find both the y-intercept, so to speak, and the x-intercept. In this case, it would be the d-intercept and the t-intercept. But they're going to have meaning behind them, and so we're going to need to find them, whether we've been asked to find them in a prior part of the problem or not. We may need to find them when we actually do the graphing. So what I did is I found it. That's what all of this is. So I set d equal to 0 so I could find my time-intercept. All right, so on this particular one, I would have had to have used quadratic formula, so that's what I did right here. Opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. I got the underneath the square root down to a single value. I then simplified that radical, so the square root of 84 is equal to 2 times the square root of 21. And then 78, 2, and 6 are all divisible by 2. So I went through, and my final exact answer is t is equal to 39 plus or minus the square root of 21 all over 3. Now, from a graphing perspective, I need to estimate what those values are so that I can graph them. So my final 2 ordered pairs that I have written over here are a result of taking 39 plus the square root of 21 all divided by 3, plugging it into my calculator, and getting that that's approximately equal to 14.5 comma 0, and then 39 minus the square root of 21 divided by 3, plugging that into my calculator and getting that that is approximately equal to 11.5 comma 0. So then what I did is I took all these ordered pairs over here and I figured out my scaling. I did label my axis, so the independent axis is the number of minutes since firing the rocket. The dependent axis is the number of kilometers from the surface of Mars. Sorry, I kind of got into my quadratic equation up here, so I had to fit that in there. And then from a scaling perspective, if I look at all my T values, so to speak, this is a 20 by 20 grid, so I just scaled my independent axis by ones. But if I look at all my distance values, I ended up scaling my dependent axis by 25. So I went up 4 units, 100, went up 4 more, 200, etc. So I got to the very top of that dependent axis, and that indeed was 500. So then, yes, I went through and I very methodically went through and graphed each one of these ordered pairs on my axis, or on my graph. And then we want to take into account, like it says modify your graph by using a dotted line for those parts of the graph that are outside of this domain. So here's the thing, we want our graph to be connected up until the point where Phoebe crashed into the surface of Mars. And then after that, our domain doesn't make any sense. So what we're going to do, we want our final graph to be parabolic in shape. This is a quadratic function, so it should look like a parabola. But after Phoebe crashed into the surface of Mars, we're going to make the rest of that a dotted line as it says, and then just continue it on. So again, it's connected and solid up until she crashed into the surface of Mars. That's going to be our reasonable domain that it talks about. And then after that, to continue it looking parabolic in shape, or in other words, to account for the parts of the graph that are outside of the domain, it's going to be dashed thereafter. So don't just, have this part of the parabola being shown. Have the whole thing shown, but make the part that's reasonable in this domain solid or connected, so to speak, and then have the rest of it be represented by the dashed part of the parabola that you see right here. All right, and then as far as answering the question, what domain would be reasonable, if we write that up here, our domain is going to be from T values between 0 and this part right here where Phoebe crashed into Mars. Now that's approximately equal to 11.5, but we want to use the exact representation of that from our quadratic formula, so that the answer that yielded the approximately 11.5 was 39 minus the square root of 21 all over 3. So this represents our domain that's reasonable in context of this scenario. All right, now just to summarize this graph, again, all of these ordered pairs were from the parts and pieces that we did above. We had this one additional component that, yes, you do need to find, and you need to show the algebraic work for finding it. And then we take all of these ordered pairs, we figure out our scaling for our graph. We identify that scaling. Obviously, we label our axes as well. And then we go through and we graph our parabola. Again, keeping in mind the parts of the parabola that are reasonable for our domain in this scenario and the parts that are not. The parts that are reasonable are going to be the connected or solid part of that parabola. The parts that are outside of the domain for this particular problem are going to be represented by the dashed portion of the parabola. All right, and one final comment before we continue is that I hope that you were pausing the video and doing the work on your own. Again, my goal in this part of the video was to guide you through the parts and pieces, but hopefully you were pausing, doing the work on your own, and then checking your answers. All right, 2 more things that I've thought of that I wanted to mention before we move on. In part D of this particular problem, we were asked to find the vertex. But if we had not been asked to find the vertex and it was now time for us to graph this parabola. Just like we went through the extra work of finding the x-intercepts for this particular scenario, we would have had to have proactively then found out what the vertex was. So again, I already had it listed over here in the points that I was going to graph because we had already found it. And then I needed to, as a sidebar here, find the x-intercepts. Well, if I wouldn't have already had this vertex determined, when I go to graph this parabola, I would have needed to take the time, just like I did with the x-intercepts, and found out what that vertex was. So in other words, when you graph your parabolas, you need to not only look at original ordered pairs that you were given, but explore what the y-intercept was, what the x-intercepts are, and what the vertex is for that particular parabola. So any of those key components that you don't have when it's time to graph your parabola, you need to do the work to find those. And then the other thing I wanted to mention is going back to our domain right here. Do notice that these inequality symbols include 0 and they include this exact value which represented the approximate answer of 11.5. It was the exact value for that. It does include those. So it's not just a less than here, but it's a less than or equal to. And the reason for that is in this scenario, the 0 represents Phoebe, before she fired up her rocket, so to speak, and that time of equaling 0 is valid. And then this exact time that represents the approximation of 11.5, that's the time in which she touched the surface of Mars, and so that is valid in this particular domain as well. So I just wanted to make note of the fact that what those inequality symbols were and why they made sense in context of this domain. Now we're on to the second part of the Day 10 notes, and I'm going to tell you where you can find these on your Schoology page. So we're going to start working with applications of quadratic functions, and if you go to your Chapter 5 folder on your Schoology page and you look under your homework worksheets, you're going to find a PDF that's called Quadratic Application Packet. All right, and what I'm going to do in this video is go through the first example, the first problem in that packet. And then you'll see on your assignments in upcoming days, we're going to assign a few of those each day out of that packet. So this is not in the Day 10 notes that we just did with the Phoebe model problem. This is actually in a quadratic application packet that will be part of your homework or assignments in upcoming days. So if you want to pause the video and go find that PDF, again, it's under homework worksheets and it's the quadratic application packet. You should see that it aligns with this example that I'm going to do right here. And then it'll be done in your packet after you watch the video and take the notes. And then again on your assignment sheets, you're going to find that we assigned some of the ones that are after this one in this packet over upcoming days. So why don't you pause the video and find that. All right, so hopefully you found that. If you notice our instructions, they say include a calculator solution and an algebraic solution, and then in the calculator solution be very specific with writing down the functions or the keys that you're using on your calculator, and I'll review what you need to write down regarding that. All right, now the approach I'm going to take for this quadratic example, this application example, is very similar to the model problem that I just did involving Phoebe. I'm going to, talk about a particular part, then I'm going to ask you to pause the video and do the work, and then restart the video and check your work. All of the parts and pieces of this particular problem that we're going to do, you should already know how to do, both algebraically and on your calculator. So I'm just here to guide you through the process. All right, so let's take a look at our scenario. All right, so we've got a projectile motion equation, h equals negative 16t squared plus v times t plus s. And it tells you that t is the time in flight in seconds, v is the initial velocity. We have two heights involved. S is the initial height in feet, and h is the height after t seconds. So after that projectile has been in motion, so to speak, for a certain amount of time, this h represents the height after that certain amount of time. All right, so specifically, an object is shot into the air from ground level at a speed of 800 feet per second. We're asked to write the equation that fits this situation. So again, see if you can, based on the variable definitions that were given up here for this particular equation and the fact that we now know that the object is being shot into the air from ground level at a speed of 800 feet per second, see if you can figure out what our specific equation will be for this projectile motion scenario. So pause the video, write down that equation, and then restart it when you want to check your answer. Our equation for this scenario would be that h is equal to negative 16 t squared plus 800, because our velocity was given to us to be 800 times t. And if the object was shot into the air from the ground, our starting height is going to be 0. All right, now, as I mentioned before, we're going to be figuring out algebraic solutions as well as calculator solutions to every part and piece of this problem. So what I would ask you to do now is get your calculator and enter this equation into your calculator. Find a suitable window for it when you graph it. So think about it. We've got a parabola that's opening down because of our negative leading coefficient here, and you want to find a suitable window for it. So we did this a while back. We entered quadratic equations and we adjusted the window so that we could see the following things. So that we could see the y-intercept, the x-intercepts, and the vertex. So pause the video now, enter this equation into your calculator, and find a suitable viewing window so that then we're ready to go for all the subsequent parts of the problem. All right, so hopefully you found a suitable window where all the important parts of the parabola were viewable. So again, the x-intercepts, the y-intercept, and the vertex. And I always encourage my students to have that parabola take up as much of that viewing window as possible. So here is a possible window for you if you were struggling with that. But again, we've gone through all the key components or features of the calculator that we're going to need for this particular problem. We went through those a while back, so hopefully you were fine with finding a window. Your window does not need to be identical to this. I just wanted to offer you a window that was suitable. So this is everything related to your x's. So, you know, the x min, the x max, and the x scaling, and then the y min, the y max, and the y scaling. All right, part B, when will the object strike the ground? So think about how we would algebraically find that. So if the object strikes the ground, that's going to be when your height after t seconds, or sometimes I refer to it as the ending height, that's going to be when that is equal to 0. So pause the video, find when the object will strike the ground algebraically. All right. And then also, once you find it algebraically, I would encourage you to then go to your calculator, think about what features you would use on your calculator to find that, go through the steps of doing that, and yes, you should get the same answer, but write down your calculator features over here. So we'll do algebraic solution here, calculator features over here. And again, I want to reinforce the following fact. All of the calculator features that we're going to be using for this problem, we did a few weeks ago when we did an introduction to you for your calculator. So think back to the features that we used and see which one would be appropriate for part B. All right, so when will the object strike the ground? That means when our ending height, so to speak, is equal to 0. So that's what h represents, as the height after a certain amount of time has passed. So we set this equation equal to 0. If we solve it algebraically, the easiest way to solve it algebraically is to factor out a GCF of negative 16t, and then the remaining part is t minus 50. So we get two answers algebraically. T is equal to 0 seconds and t is equal to 50 seconds. Now the one we're going to have as our final answer is t is equal to 50 seconds, because that's when the object, after it has been launched, is going to strike the ground, 50 seconds after it was launched. All right, now what this represents, these are the x-intercepts, so to speak, or the time intercepts, if we want to think about it that way, since we have the variable t right here. So to find those on our calculator, hopefully you recall that we do calc 0, And then we are asked 3 questions for each x-intercept. We're asked, or each 0, we're asked to establish a left bound, hit enter, a right bound, hit enter, and then hit enter one more time, and it will give you the x-intercept, or the 0, and we have 2 of them, so you would have to go through the process 2 times. You should get 0, 0 and 50, 0, and then once again you interpret your answer, and your final answer would be 50 seconds. So what you need to do over here for the calculator part is you need to write down the calculator function that you used. You need to write down what your calculator told you, so to speak. So you found 0, 0 was one of your zeros, and 50, 0 was your other 0. And then you need to interpret your final answer to answer the question. So again, we're going to throw out the answer of 0, 0 in this case, and we're going to keep the 50, 0, so our final answer is 50 seconds. Again, our algebraic answer and our calculator answer will not be any different, but it's a difference in how you show your algebraic work versus what you show from your calculator. Part C, when will the object reach its maximum height? And then we're going to do part D along with it. What is the maximum height attained by the object? So if you think about it, we have a parabola, and it's pointing down, so to speak, opening down. So if we think about it graphically, it would be starting and then going up and reaching a maximum height and then coming back down. So when it reaches that maximum height, and what that maximum height is represented by the vertex. So it's asking us in part C and D to find the vertex. So pause the video, find your vertex algebraically, also find your vertex via your calculator, and then restart the video and check your answer. All right, let's see how you did. So algebraically, when will the object reach its maximum height? So I just rewrote the quadratic function right here. So for our time element, okay, t is going to be equal to the opposite of b all over 2 times a. And then that will yield an answer of 25 seconds. So that's when the object reached its maximum height. Then if we put that together with part D, what is the maximum height attained by the object, at that time? If we take that 25 and we plug it into our original quadratic function, so plug a 25 in for t, and again, you can just show that work and then plug it directly into your calculator. H is going to be equal to that height, that maximum height is going to be equal to 10,000 feet. All right, now before we look at the calculator part, let's talk about what we just found. So keep in mind, we've got this quadratic function, and we've got an object that started at the ground, all right? It was projected up into the air, all right? And then it is coming back down, so to speak. And since it's quadratic in nature, or parabolic in nature, it's going to go up into the air, it's going to reach a maximum height, and it's going to come back down. So it reached that maximum height of 10,000 feet 25 seconds after it had been launched. All right, and now if we look at the calculator portion of it, to find a vertex, we're going to, on our calculator, since this is a parabola pointing down, then we're going to calculate the maximum. If it was a parabola pointing up, we would be calculating the minimum, but we use the Calc Max feature of our calculator. And again, we have to go through a series of 3 questions. So we establish a left bound and a right bound, and then we hit enter one more time, and you should get the answer of 25, 10,000. And when we interpret that, it means that our maximum height is reached at 25 seconds, and that maximum height is 10,000 feet. So what you need to write down is the calculator feature of Calc Max. You need to write down what your calculator told you, and then you need to interpret the answer. Again, the calculator answer, once you interpret it, should be the same as the algebraic answer, but we want you to be able to do both. All right, part E, when will the object be 51 feet above the ground? So if we think about that algebraically, this is where the ending height would be equal to 5,100. So from our original quadratic function, that's where that h value is equal to 5,100. So the starting height was 0 because it started on the ground, the object started on the ground. The ending height after it ends, where it ends up after a certain amount of time has passed, which is represented by the variable h, is going to be 5,100. So pause the video, plug a 5100 in value in for h, go through and solve that algebraically. Then think about what calculator features we used in the past to achieve an answer or a scenario, like that, because we have talked about that. Go through, do all your work algebraically and with your calculator, then restart the video and check your answers. All right, so let's see how you did. When you plug a 5100 in for h, in order to solve that, you need to get your equation set equal to 0. Now, believe it or not, this one actually factors. So I'm going to go through the factoring part, and then I'll talk through quadratic formula too. But you could factor out a GCF of -4, and then make your adjustments here. So you would have 4t squared minus 200t plus 1,275. And then this quadratic trinomial actually factors into 2t minus 15 and 2t minus 85. If you set those factors equal to 0 and solve, you're going to get that t is equal to 7.5 and 42.5. Now let's say you didn't realize that factored. Let's say you use quadratic formula instead. You could use quadratic formula straight from the beginning. That's fine. I, though, chose, since I already factored out a GCF of -4, I chose to use quadratic formula based on this remaining quadratic trinomial. So my quadratic formula down here is based on this quadratic trinomial right here. So if you go through and plug everything into quadratic formula, I don't need to read you the numbers, you simplify everything under the radical, you get this lovely value right here, 19,600. Now, I am confident that that further simplifies. But here's the thing. We don't need your answer as an exact radical format, so to speak. But if you kept simplifying it, so to speak, you would still end up with the same answer up here. You would end up with t equaling 7.5 and 42.5. So once you get it down to a single number underneath the radical for this one, you can plug it into your calculator. You don't have to worry about simplifying it more as a radical. Just plug it straight into your calculator and you'll get your 7.5 and your 42.5. And finally, before we talk about the final answer, if you were to use quadratic formula straight on this part of the quadratic equation up here, before you factored out the GCF of -4, you would still get your final answer of being t equaling 7.5 and 42.5. All right, so when will the object be 5,100 feet above the ground? At time equaling 7.5 seconds and 42.5 seconds. In this particular case, it's okay to get two answers as our final answer. And if we think about it, we've got this quadratic function that represents an object being projected into the air. And we know that it's a parabola pointing down. So this object is traveling up into the air, it's reaching its maximum height, and then it's coming back down. And this height of 5,100 feet, if we were to graph it, it obviously is a horizontal line. And in context of this scenario, it can be that, and I don't necessarily have this drawn to scale, but this object is taking off from the ground, it's going up and reaching its maximum height, and it's coming back down. It could reach that height of 5,100 feet on its way up to its maximum height, and it could reach that height of 5,100 feet on its way back down. And indeed, that's what happens here. 7.5 seconds after it's been launched, it reaches that 5,100 feet above the ground, that height, at 7.5 seconds after being launched, and then it reaches it again on its way back down, which is 42.5 seconds after that object has been launched. Now let's take a look at the calculator feature that would help us get this answer. So in our y sub 1, we have the original function entered, and then in y sub 2, if we enter 5,100, when we graph that, again, we would get our parabola pointing down and we would get a horizontal line being graphed. And if we do calc intersect, and we talked about that feature a while back, if we do calc intersect, and again, we're asked 3 questions, but if we do calc intersect both on this intersection point right here, we'll get 7.5, 5,100. If we do calc intersect again on this intersection point over here, we'll get 42.5, 5,100. And then if we interpret our final answer, we will get the same as we did algebraically. So that time would be at 7.5 seconds and 42.5 seconds when that height of 5,100 feet above the ground would be reached. All right, so in summary for this quadratic application problem that we just did, I cannot emphasize enough how much I hope you pause the video and for yourself, answer these questions algebraically, and then took the time to enter things on your calculator and use the calculator features so that you could then check your answers and take a look at what the algebraic answers look like and what the calculator answers looked like, as far as writing down the calculator features that needed to be used, as far as what answers your calculator gave you, and then interpreting your final answers. We're going to be asking you to do the things in this packet both algebraically and with a calculator. Obviously, the answers should not be any different, but we want you to get practice with solving, and answering the questions algebraically, and then using your calculator features, writing down the key calculator features that you used, the answer the calculator gave you, and then interpreting the final answer. So as you're working your way through this packet on various days as far as the assignments being given, make sure that you're doing both the algebraic work and the calculator features. Hopefully you practice that via this video and didn't just watch me do everything, so to speak. All right, so this wraps up our day 10 video.